Hello, chemist and biochemist. Today's video is going to be focused on demonstrating how to calculate the isoelectric point, also known as the pi of a tripeptide. Now, I'm not going to draw this molecule. I'm not going to draw this tripeptide. However, I'll use I'll use some simple tricks so that you can kind of visualize the molecule. Okay. Now, the tripeptide that we are going to draw is AKD. What that means is that our N-terminal amino acid is an alanine. Our an alanine. Then after that, there is a lysine, and then on the C termini is an aspartic acid. Now, when you look at that tripeptide, or when you think about that tripeptide, you have a total of 3 amino acids. Only 2 of them have ionizable side chains. So what I always like to do whenever I'm confronted with a problem like this is ask myself, what is the pi? What I also like to do is I like to go ahead and imagine this molecule at a pH of 1. Now, the N-termini, I'm going to go ahead and draw a little box around this. The N-termini of the alanine is going to have a positive charge at a pH of 1. The side chain for alanine is going to be neutral at a pH of 1. The R group, or the side chain for lysine, is positive at pH of 1. The C termini has or C-terminal amino acid, R group for aspartic acid, is neutral at a pH of 1, and so is the C termini of my peptide. So why I like to do this is this shows me my extreme pH, a very acidic pH, where everything that can be protonated is protonated, has a charge of +2. Now, I'm going to go ahead and list out my pKa values for all of these ionizable groups. The C termini has a pKa of 2.77. The R group for aspartic acid is 3.65. The R group for lysine has a pKa of 10.53. And then the N termini for alanine is 9.65. Now, what's important is that these values, these pKa values, they're going to vary a little bit depending on the resource that you use to get them. Now, what I'm going to do is I'm going to think about the fact that this has 4 groups that are ionizing. 4 groups that will either go from positive to nothing or nothing to -1. What that means is that my molecule will go from a +2 charge to a +1 when the first group is deprotonated. The first group deprotonated is the C termini of the aspartic acid. The next group to be deprotonated is the R group for aspartic acid. And when that group is deprotonated, I have a molecule that has a zero overall charge. The next group is going to be my N termini of my peptide. My final group is that R group for lysine. So my molecule will go -1, and then from -1 to -2. So this molecule has a total of basically 5 different forms that it can take, and there are kind of 4 transitions. So because there are 4 pKa values, I like to represent the kind of spectrum of charges. And then what I like to do is I like to think about it, okay, well, when is this going to change from a +2 to a +1 form? Well, whenever we are at or around the pKa, or when the pH of my solution is at or around my 2.77 pKa. Next up is 3.65. That's when my molecule is going to transition from +1 to 0. My molecule will transition from 0 to -1, not until my pH is around 9.65. And then the last pKa that I'm going to list, 10.53, is where my pH when my pH is equal to 10.53, do I have an equal ratio of the -1 charge form of the molecule and the -2 charge form of the molecule? Now, all of this information is helpful for me, but do I need all of it? And is all of it really essential for me to do my PI calculation? The answer to that question is no. What I need is what are the two pKa's that are found when my molecule transitions from +1 to 0 or 0 to -1. And I've got 3.65 plus 9.65. Those are my two pKa values that matter. Now, what I'm going to do is I'm going to add those two up and divide it by 2. What this is going to give me is the exact midpoint between those two pKa values, which 9.65 plus 3.65 is going to be approximately 13.30. Divide that by 2, and you end up with 6.65. Okay, so my pH equals 6.65. What that means is that 100% of this molecule has a 0 overall charge. Now, one way to look at that also is to think about which of my ionizable groups are deprotonated. Well, the answer to that is, and where are my charges actually going to be found? Because although the overall charge is 0, there are still charges on this molecule. For instance, the N-termini still keeps a positive charge. My R group for lysine still maintains a positive charge. My aspartic acid R group or side chain has a 0 charge, and my C termini of my aspartic acid also has a negative charge on it. So there are still charged portions of this molecule, but the overall charge for this molecule is 0. So at a pH of 6.65, 100% of the molecule looks like this right here, an equal number of positive and negative charges canceling one another out. All right, well, I hope this is helpful. The same thing applies for a tripeptide, a tetrapeptide, pentapeptide, dodecapeptide, and a single amino acid. What you need to do is find the two pKa's that flank your 0 overall charge. So when you see what pKa gives you a molecule going from +1 to 0, what pKa gives you a molecule going from 0 to -1. That's all there is to it. I hope this was helpful. Have a good one.